Well, I hope you can hear me all right. Good morning, everyone. It's an honor and pleasure standing here today and to talk about thrifting and recycling of platinum group metals being core elements for a growing hydrogen economy. Before I'm going to start, let me say thank you to the organizers for this great and wonderful event. It's a real pleasure being here. And I will start now the presentation first by introducing Heraeus briefly, and then dig a little bit deeper into the PEM market development. And then I will actually talk about thrifting and recycling. So Heraeus is a family-owned company in Germany. I think we have been formed in 1851, so we are around since quite a while. You see here our innovation center. It's named 51. Some people say it's the Area 51. It's not true. It comes from the founding date, 1851. And we have several businesses within the Heraeus group, and one is, and the oldest one, is precious metals. And I'm with Heraeus Precious Metals, and precious metals are in our DNA, platinum group metals as well as silver and gold. And what we do is basically we have these three pillars in our business. It's trading, it's products, and the recycling. Oh, wait, oh yeah, okay. Of course, we're also based here in China. We have our head offices in Shanghai. We have a plant, a big one actually in Nanjing since 2015. And we also actually recently formed a joint venture with BASF here on the AutoCAD recycling. That's Heraeus basically in China. And what I would like also to mention is decarbonization or sustainability is close to our heart. We do a lot with respect to decarbonization. Our target is to become carbon neutral by 2025 concerning Scope 1 and Scope 2 emissions. And actually we came a long way compared to 2019. We reduced our Scope 1 and Scope 2 emissions by 41% until now, despite a growing business. So that's a real achievement, and we are still targeting 2025, as I said, to become carbon neutral, and by 2033 we will reach net zero emissions and only with less than 10% offsetting, and the Scope 3 emissions we want to reduce together with our partners apparently by 50%. And also in China we are doing a lot in terms of decarbonization. So year over year, we have around 13 to 40% energy saving. And we actually use 100% green electricity. If you ever had a chance to visit our plant in Nanjing, you see a lot of photovoltaic panels. So I think we are in a good way here also in China. With this said, I'm sorry, this always takes a little bit longer. Here we go. With this said, today's topic is electrolysis. Platinum group metals, and I start by talking briefly about the electrolyzer market development, and then about thrifting and PGM recycling, and maybe also the recycling of other components. If you look into the IEA, International Energy Agency database, you see that there are around 1,653 projects announced globally. That's a status October 2023. And this amounts to an overall capacity of 825 gigawatts. That's an enormous figure. If you dig a little bit deeper and you check which technologies are actually shall be used, and we have the proton exchange membrane electrolysis, we have the alkaline electrolysis, AEL, and also solid oxide electrolysis, and you see that the majority of these projects are actually undecided in a way which technology will be deployed. And the electrolyzer capacity, with respect to the status, you also see that many of the projects, they lack still the FID, the final investment decisions. And that's actually something which you notice globally. In order to move forward, these FIDs have to come. So how does it look in China? 29 gigawatt of electrolyzer projects have been announced in China, according to the IEA database in October last year. The FID, the final investment decision ratio, is higher in China compared to the rest of the world. And you also see that the proton exchange membrane electrolysis plays a pivotal role here. with a significant share. And even 2% of all the projects are actually already operational. So I think China is leading the way here when it comes to setting up electrolyzers, also PEM electrolyzers, not only alkaline electrolyzers in China. In the market, there are three main topics. It's actually the thrifting of PGMs to reduce cost and also with respect to the availability of iridium, the recycling of end-of-life stacks and the production scrap is increasingly becoming a topic. So we get more and more requests also from larger OEMs. Can you help us with recycling? And the role of PGMs in other electrolyzer technologies than PEM is actually also increasing. So you usually, when I started this role 5-6 years ago, everybody said, no, alkaline electrolysis, there are no platinum group metals. And I think this is changing because some of the players are looking more and more into using platinum group metals, which is understandable because in these gigawatt arrangements and the high current densities, you actually need other materials than nickel. Thrifting of PGMs. If you look into the cost of electrolyzers, a significant reduction is needed to actually be able to produce hydrogen at scale in an attractive price. There are various activities in order to reduce the cost and the capex actually from $1,000 to $1,500 per kilowatt down to 500 to 700 kilowatt. That's actually from the Fraunhofer Institute. They predicted this is a capex you need in order to become competitive. And you do that by either advances in stack performance and design. We should not forget that. It's not only about the catalysts. Economies of scale will play a role, but last but not least, also new materials and the reduction of the PGM loading. So platinum and iridium are both used in PEM electrolyzers. On the cathode, you usually have a platinum compound. On the anode, it's usually iridium. So for the oxygen evolution reaction on the anode, that's basically where you need iridium. And it has started with iridium black, metallic, finely dispersed iridium. And then iridium dioxide is a second generation, which was actually put forward a couple of years ago. And now the latest developments basically from Heraeus allow a further reduction of the iridium. From iridium black to iridium dioxide, you simply replace iridium by oxygen. In the iridium oxide on a carrier, you have a general catalyst concept. What you basically do is you have a carrier and you put the iridium or the iridium oxide or hydroxide only on top, on the outer surface of a particle. And that, of course, is where the iridium is needed. It's not needed in the core of the particle. And then, last but not least, in October 2023, we launched actually mixed oxides, ruthenium-based catalysts, iridium-ruthenium mixed oxides. And here you replace iridium with ruthenium. Ruthenium actually has been always claimed to be not stable enough. Electrochemically, it's even more active than iridium, but it lacks stability. But by combining these two elements and put that in a special way, basically into the structure of the iridium dioxide, you actually can achieve both high activity and high stability. And what you do, you reduce the loading of iridium by up to 90% compared to the iridium black. And it is commercially attractive. We are talking about reduced metal cost, of course. We're talking about the reduced input power due to the 10 times higher mass activity of this mixed oxide catalysts. And further savings are, of course, happening through optimization of the equipment. Recycling. So if you look at proton exchange membrane, fuel cell, and electrolyzer stacks, what's shown here is a composition by weight. And you see that platinum and iridium are not contributing a lot weight-wise. It's still steel and aluminum are dominating elements by weight. And this composition you see here is always subject to change. So that's basically the electrolyzers or fuel cells you get for recycling these days. Of course, technology is advancing, and maybe modern proton exchange membrane fuel cells and electrolyzers can have up to 30% less PGMs inside. It's simply the latest technology. Looking at it now from an angle of material value, PGMs represent the highest material value in a stack, up to 90%. Again, that is not the latest technology, but that's basically what you get for recycling these days. And the other topic, when you think about recycling, there is a value in these PGMs apparently, but what about a functional value, for example, of bipolar plates? Can you reuse them? What about porous transport layers? What about the ionomers, the membranes? Can you reuse them? And that is something, of course, which we are also looking into, thinking now here about the standard PGM recycling from catalyst-coated membranes that already exists. It's standard business for Heraeo's precious metals. You incinerate the membrane, you do wet chemical treatment, so you separate your platinum group metals, and you end up with a refining to make a highly concentrated platinum and iridium. There's a strong advantage because the homogenization of the ash and the assaying is very easy, I would say, when it comes to this kind of process. The carbon footprint, I show you two numbers here. From the incineration with natural gas, you're talking about 6.7 kilograms per kilogram CCM. And with our latest new electrified furnace, you're down to 5 kilograms per kilogram CCM. Why is it not significantly less? You still need, for the off-gas treatment, you need still natural gas, which basically cannot be electrified due to the high temperature so far. Critical is, of course, you reduce or you destroy the value of the ionomer, and you need a proper furnace design and a suitable exhaust gas treatment because these ionomers are fluorine-containing compounds, basically, and fluorine is very aggressive. So looking into another wet chemical process to recycle the ionomer and the catalyst-coated membranes, you can still get to very high platinum and iridium values. It is the process is basically there. The carbon footprint in ionomer recycling is actually higher with the wet chemical process compared to the incineration. We are talking about 23 kilograms CO2 per kilogram CCM. It only is lower if you have a beneficiation through the reuse of the ionomer. And that is the critical part, because the challenge is, can these ionomers be reused, and for what can they be reused? And the availability of end-of-life stacks to really test this with real ionomer material, which was used in an electrolyzer or a fuel cell, that's missing. There are not so many spent stacks available, which makes it difficult to come to a case for the ionomer. And there's one additional issue. Well, we think we have a solution, but taking a representative sample without incineration is another challenge, but there might be a way around. So then there are other stack components. There's a drawing, basically a schematic drawing of a fuel cell or an electrolyzer stack, and you see you have the end plates, bipolar plates, porous transport layers. Some of them actually can contain platinum or gold, bipolar plates or PTLs, porous transport layers. And the recycling of platinum from these components, there are various options. This also needs to be worked out in the end. Mechanical treatment, pyrometallurgical treatment, electrochemical platinum dissolution, or hydrochemical platinum dissolution. So these are all options to deal with PGM-containing components like the bipolar plates or the porous transport layers. So I'm already at the end because I clearly recognize it's me standing between you and the coffee break. And let me quickly conclude about this speech. PEM technology will be an important technology for hydrogen generation. I think this is given, as will be platinum group metals. And in order to move this forward, the overall PEM technology thrifting of PGMs is required, and solutions are available to support cost competitiveness of PEM stacks in general. The major value of PEM stack recycling isn't the precious metals or in the platinum group metals still, and functional use and value of recycled ionomers and other components need to be determined. And with this, I want to close and say thank you very much for your attention, and I'm looking forward, if there are any questions, we can speak later during the coffee break. Thank you very much.